but it brings to light another point, a second question I had. In the causal set world, these events, at what point do we imagine that the idea of a particle emerges? Because you mentioned quantum field theory. We think we know how to do quantum field theory in the continuum, but that presupposes that we have this arena on which particles and fields existed. And when I think about causality and events existing, whether it's in this quantum version of a causal set or in the continuum, I think of event as being, for example, the electron was here, or this photon interacted with this electron. That's because of my upbringing and my education, and I'm sort of set in the way of creating an event. But in this version of making a continuous manifold from a discrete causal set, or even a set without any particular ordering, I imagine initially that those events labeled things that made sense to me, but it becomes more apparent as I think about it that you can't do that. So is there any idea talked about in this field of research by which after the discrete set creates a manifold, at what point do we imagine that particles and fields made sense to put on it in the first place? Did they exist in the discrete version of the manifold and then also crystallize into what we see? How does that come into existence in this paradigm?
We're keeping an open mind about how matter is going to be described within the causal set framework. Either we'll need to add extra degrees of freedom on top of the causal set as well as the causal set. So, for example, we have a model of a scalar field theory on a causal set. So that's an example where we're adding extra degrees of freedom. Or it's possible that and we have models of particles moving on a causal set, for example. Again, you're adding extra information on top of the causal set. Or it could be that there's only the causal set and that matter will have to emerge from the causal set. The data of the causal set will have to contain the matter degrees of freedom as well as space-time degrees of freedom.
Right.
And there's a sketch of how that might happen whereby gauge fields arise as from Kaluza-Klein reductions.
I was just going to ask about Kaluza-Klein theory. Could it be that
and fermions could arise as topological geons, but they would kick in then at a much higher level, that they wouldn't be present in the fundamental discrete causal set, but they would emerge as a sort of intermediate regime between the discrete regime and our known physics. But it would be already a continuum regime. So, yeah, thank you for your question.
Kaluza-Klein theory kind of makes sense for that, because it would all the fields that we observe would then be part of the geometry that just came into existence. At least that's kind of the direction I would hedge my bet.
Yes, that would be lovely. If everything, if that would be the ultimate unification of matter and space.
Yeah. Well, thank you very much. Your answers were satisfactory, even though this field is still growing. It's the direction that we kind of naturally think in terms of quantum field theory. But I wonder if anyone's giving serious thought to whether that's kind of an anthropomorphic line of reasoning. That is, we're here, we observed this, we created this, and so now we're creating a cause for the thing that we know we have to see. I suppose that's more a philosophy question.
I have a fairly elementary question. So in the talk, did you tell us how we recover the metric structure of space-time? That is the amount of distance between different points instead of just the topology?
Thank you for the question. No, I didn't. I just made the very, very quick claim that a causal set can encode Lorentzian geometry, and I didn't tell you how. So the confidence that that's the case is based on a theorem in the continuum that says that if you know the causal order, that is, all the information about which point events in this continuum space-time are in the causal past of which other point events, all of that. So if you like, just the light cone structure of the space-time, if you know that, and you know the space-time volume element, in other words, the square root of minus g d4x, that then you know the full geometry. There's some technical conditions for that theorem, but so the theorem is due to various people over the years, but Penrose, Hawking, and Malamant are the main prove the sort of main results that lead to this theorem. So, and the space-time has to satisfy a certain causality condition. So the idea is that a causal set it contains the causal order information, because that's exactly the order relation, and it contains the volume measure because you have the counting measure. It's not a continuum, but you can just count. So you have a counting measure which gives you the volume measure, and that, the theorem suggests, is enough to give you the space-time geometry, the full geometry, on scales large compared with the discreteness scale. So it won't tell you the geometry on scales smaller than the discreteness scale, which is hypothesized to be the Planck scale, because it can't. I mean, but on large scales compared to the discreteness scale, the order relation and the counting measure give you the full geometry. That's the idea.
Can I just quickly follow up, Nick? Okay. So that helps. So just to be clear, when you talked about the counting measure, when I thought about those diagrams that you drew, there's no natural sort of background on which it's drawn, right? You could make them as sparse as you please. So right. I don't know how you would define a density of points without sort of a background measure already in play.
So the density is 1 in natural units. So that we don't know precisely what the fundamental unit of 4 volume is. We think it's of order the Planck 4 volume, right? So that's the Planck length cubed times the Planck time, roughly. So that, in fact, that's a concrete dynamical question for causal set theory. What is the fundamental volume in Planck units, right? In centimeter cubed seconds. Something of order 1 is the hypothesis, the working hypothesis. But the idea is that sort of it's the other way around, right? There's a fundamental scale, and the density is 1 in fundamental units. But how does that translate? What is it in centimeters and seconds? That's a dynamical question that we can only answer once we know how matter fits into the picture, as per the previous question. So what is a centimeter in fundamental units? That's the question. What is Newton's constant in fundamental units? Those are hard dynamical questions that the theory will have to answer in the end.
2 questions, I think, and at least one of them is just born out of ignorance more than anything else, and so I was hoping you could fill it in. And that's, so the theorems that you gestured at all seem to have to do with sort of limit results on these stochastic processes. And I'm wondering to what extent that sort of method is too blind to the things we care about in these cosmological models. And what I have in mind here is something like, well, I'm often not interested in the long-run probability that any particular stem will be there, but I'm interested in the relative frequencies that I'm getting around me for these different structures. And so is that just, there's a different program going on along the side that looks at those questions, and your talk was centered on the long run stuff? Or is there a specific reason why these are the sorts of results that you're presenting?
We don't know how to even ask the question you're asking, because general covariance, this label independence, causes an enormous amount of trouble, because the sort of thing you would like to ask, and I agree that we would like to ask, I mean, that we should be asking, that we want to ask is, given that let's say my past was such and such, so that, there was a stem which was like this, say the past which corresponds to our observable universe back to the Big Bang, say, what's the probability that in the future such and such will happen, right? So in other words, what's the probability of a particular stem, given that there was a substem with a particular structure, something like that, right? So that would be those are conditional probabilities. The problem with that is that it's what we call, it's a bugbear of ours. We call it this stem problem, because there's no way, there's no covariant way to distinguish different copies of the same stem in a causal set. So we want to know what happens here when our stem was such and such, and we want to know what's the future for us. But if you ask the question, well, so conditional probabilities in a stochastic model are, they're calculated by reducing the full sample space down to the sample space where of just the event, which is the condition, right? So you just throw away all the causal sets that don't have that stem. But the problem is that there'll be causal sets in your event which have that stem in multiple copies, here and here and here and here, in the same causal set. And then you're asking, well, what's the probability that the future of one of these stems is something? But you don't want to know about the future of one of them. You want to know what the probability of the future of our particular copy of that stem is. And that's something that I'm not even sure whether any of us have written that down in print anywhere, because it's kind of embarrassing. I mean, it's embarrassing for us, but I think it's also embarrassing for everybody who is because of general covariance. It's if your model is random, if there's randomness in your model, whether it's quantum or classical, it's randomness, so it's not a deterministic model, then you have to grapple with this, and your model is covariant. That is, it doesn't, you're not allowed to use labels as physically meaningful. Then everyone will have this problem. So it's embarrassing for us, but it's embarrassing for everyone. We don't know how to answer that. I mean, we've toyed with the idea of, well, you have a marked stem, but what's the mark? What's anyway? Yes. So a fantastic question, and we can't answer it.